All right. Can you see my screen? Okay. So today, yeah, so I think we're basically done with lecture, and I wanted to go over mostly a couple fundamental problems that I feel like are fairly important. So yeah, today is going to be mostly problem solving. Um, and for my plan for next time is to actually go over one of the more recent exams in full and just spend next, so Friday, just going through one full exam and solving all the problems. Um, okay, so let's start doing, I think, again, one of the more important things to focus on for this exam is how to basically just use dominated convergence and Fatu a lot and how to understand when those fail. So let's do the following problem. This is number, what is it, 4 in the LP. So this is LP spaces and density. Okay, so the problem is the following. So let B in R D be unit ball. Okay, and I have a sequence of FK, which are all positive. And I have the following condition, or two conditions. So A, so such that A, FK converges to F almost everywhere. So it's a convergence problem. And B, I know some sort of regularity of this family. So this one's FK, X, DX, less than epsilon. Dun, dun, dun. So this happens for FK greater than or equal to M. So the correct statement is this. So for all epsilon greater than 0, there exists an M, possibly very large, such that this happens for all K. Okay. Is it clear what these conditions are saying for the problem? Okay, cool. So what we want to show about this is show Fk converges to F in L1 on the ball. Okay. So in some sense, this condition is not enough, right? We got to use something else to show convergence, as always. So we end up using this condition, which is a form of uniform integrability, right? It's similar to the other problem we saw maybe like last week. But let's go through it really carefully because I think it uses all of the things you want to use for these problems.
Should there be an absolute value of FK in that
They're
integral
all
or
positive.
something?
They're all
Oh,
positive.
oh, okay.
Yeah, yeah. Good. Yeah, it wouldn't be true. Yeah, let's think about that later. So you could put absolute values here, but it's positive, so not. Okay. So one of the first things we want to do is use this condition B. So whenever you see a condition like this, where I have level sets, right? The idea is in order to control this guy in L1, so I need to control Fk minus F on the ball. The best way to do this is I split up the ball into places where Fk is greater than M and places where Fk is less than M, right? To use my condition. Okay. And this is of the difference Fk minus F. Okay. And so on the part where I'm above this point, right? Well, I can do a few things. So okay. So what I can do is I can check that, okay, if I'm greater than M, okay, I should do this. So there's a few things I want to show. If I'm bounded by M, right, I can somehow apply bounded convergence theorem to this part. right? So when I take a limit for any m, I know that this guy goes to 0, right? Because of convergence like this. Um, for this part, I need to somehow use that this is small. So my smallness condition up here, right? So there's a part which is bounded below, and then the part which I don't have any control of, but I have by my condition small. So things to check. So I'll call this integral 1, this integral 2. Okay, for integral 1, if I'm greater than or equal to m, then I know that this guy is small. But also, I know by fatu that actually f is going to be small. So let's check that. So in particular, if I take fk minus f over this set fk greater than or equal to m, this is going to be less than or equal to fk, because fk is positive, on the same set, plus integral of f, b fk greater than or equal to m. Now the idea is I want to use fatu to show that, okay, if I know this guy is small for all k, then I should be able to take a limit, right? So fatu says that the integral of f on this set right is, how do I want to say this? Okay, I want to say that the lim inf of this guy so I know that this is equal to f, right? But when I integrate this on b, so this guy is less than or equal to lim inf of fk. Okay, and so what I want to say is that if this guy is, if I take this intersection, fk greater than or equal to m, fk equal to m, uh, there's a k dependence here, so I need to somehow put this back inside the function. So the way I rewrite this to apply fatu is the following. So I view it as the lim inf of the characteristic function of ak, right? Where ak is this set, because these sets are changing as I change k. And so when I look at this is going to be this guy. And I want to say that these guys converge to f greater than or equal to m as k goes to infinity, right? Because they converge pointwise almost everywhere. So this guy should converge to characteristic function of a. This guy is a. And so this is the statement I'm aiming at. So what I'm doing is I'm including the cutoff, right, as a characteristic function. So by fatu, so fatu is this line, so the lim inf I can pull outside of the integral. It's a positive function. This shows that the integral of f of, and I'll just write it here as, so this is b intersected with f greater than or equal to m, is less than or equal to lim inf a goes to infinity of this guy. So b intersected fk, right? But I know that this guy is always less than epsilon if m is large, right? By our condition above. So this condition. Okay, so I've taken care of this term, the one without k dependence, and also this term I already knew how to handle, right? That's the condition. So what I've shown is there exists an m such that the first integral, the one where I'm above a certain threshold, is less than or equal to 2 epsilon, right? So I pick up an epsilon from this part and from this part. Okay, so the only thing
Can I ask
left
you a
is,
question?
yeah.
Don't we have fk greater or equal than m in the term that we want to control, but just f greater than m in the other one? So the two sets over which we integrate aren't exactly the same. There's still an fk there,
Mm-hmm.
and there's no
Let me see.
fk.
Yeah, yeah,
Just
yeah.
this.
I see what you're saying. Okay, let me think. So, okay, this argument shows that f on this set is small. You're right. But this is a different thing. Um, however, if I take the limit, right? So what I've shown is, you're absolutely right. So this guy, yeah, I'll walk through the steps. So I have the integral of really the set I care about is this, b intersected fk f. That's what you're saying, right? There's a k dependence here. Okay, so what I do is I rewrite this as being the integral of a characteristic function of, again, ak, just using my shorthand, right? And so I actually know that this guy is still, so I know that this guy is less than or equal to f, which is an L1. And AKF converges to A as K goes to infinity. So apply dominated convergence. So what this means is when I take,
Can you remind me why is f in L1?
that's part of the assumptions. Let me think.
Is it?
F
No,
is
it's
an
not.
L. You can show F as an L1 using Fatou's lemma very
So you can show,
straightforwardly.
yeah, if I pick, yeah, so F is in L1 because of that too. If I just forget about the characteristic function here, right? I have that the integral of these guys is, do I even know that these are bounded? No, I don't.
You can maybe split
So,
over the
mhm.
set when fk is large and then apply for 2 to show
Ah,
that f is in L1.
hmm hmm yes. So, yeah, so you're splitting over, you basically have to check that F is in L1 first. So I'm splitting over the set where, yeah, let's walk through it. So check F is in L1. So if I have integral of F, I know that this is the integral of lim inf Fk on the set where F is greater than or equal to M. Da, da, da. I'll put it here. Plus, how do I want to say this? I want to say something like this. So this is the set where I would like to show.
So you can write the integral of f as like
Mhm.
an integral over where the two sets where f is small and where f is large. And we
Mhm.
showed above that on the set where f is large, the integral, the limit of the integral is can be controlled. And
Mhm.
over the other set, we have like that f is small and then the unit ball is finite measure.
Yes. So this set is the one we care about. Yeah, sorry, I'm getting there. Been a long day. Okay. Yeah, I see what you're saying. So the idea is that if I'm bounded here, is what you're saying, I'm good. So if I split it like this, I'm good. The part where I'm above M, what I have is this guy. So I know that this is right. So I get that this guy, let me rewrite it carefully. F is less than or equal to this of F. And I know that that term's good. And then this term is, so this is less than B times M, right? Plus, and then this other part is epsilon for M large enough. Okay, so this is good. So we're in L1. And so I know that uh, these guys converge. So I know that this happens, right? Okay, so what this shows is that when I go back above, okay, I have two parts. Let's go recall what happened. So I have a part where I'm above M. I checked that F is in L1, right? When I'm above M, I can bound this difference by this term, which I know is already good by my condition, and then this other term, which I can approximate by when I integrate over the set where F is greater than or equal to M, right? So then I have this. Okay, so that still shows that when I take k to infinity, that the first term is good. For the second term, I'm actually bounded. So I can apply dominated convergence to it, right? Because if I'm on this set here, each of the FKs is bounded, right? And I know that F is integrable. So let's walk through the argument. So really what I care about is this guy. Okay. So for 2, it's this. But I know that Fk minus F times this characteristic function is less than or equal to M plus F, which is in L1. We already checked this in L1. Right? So these guys, when I take a limit, so I can apply dominated convergence here too. Does that make sense? Because that somehow this is the easy part. I'm bounding all the behavior. So the way you apply dominated convergence is, okay, 2, when I take the limit as k goes to infinity of, and then it's the b characteristic function of ak, that's what I've been calling it. So I apply dominated convergence. I know that this is exactly equal to the limit, but I know that this limit is 0, right? Because Fk converges to F almost everywhere, which is 0. So in total, when I take the limit of these guys, so uh, I can show that it's less than, so given epsilon greater than 0, there exists an M depending on epsilon, such that when I take this integral, Fk minus F, on the ball, and I take its limit, right? I killed a bunch of terms, but I know this is less than or equal to. Well, I had 0 from the part where I'm bounded, this part. Then I go back up and I check that, okay, I had a term which was this term, which I knew was bounded by an epsilon. And then the other term, when I took a limit as k goes to infinity, is also bounded by epsilon. So I got a 2 epsilon, right, from this contribution. So I know that this whole thing is less than 2 epsilon, which implies that that this guy is 0, right? So I should say the lim sup, because I don't know if it exists. So this implies that fk converges to f in L1. Okay. Sorry if that was a bit messy at the beginning. You're absolutely right. We needed to check that f was actually in L1 first, in some sense.
Can I ask you another question?
Yeah, go for it.
So when I tried this question on my own, I thought since we have almost everywhere convergence, for k large and arbitrary epsilon, there's a set of measure one where f is arbitrarily close to fk.
Yeah.
And I try to use that to show both that f is an L1 and that and then didn't have to use Fatu, just the condition, because like
Yeah, in some
I
sense,
didn't have f anymore. I
yeah.
bounded with two absolute value of fk.
Two absolute. So you
Does
were
that make sense?
you were using this. You were using something like this guy.
Yes.
So yeah, this is one thing that's really different.
Plus
So
some
for some
epsilon.
plus some epsilon.
And then
Okay.
let the epsilon goes.
So you don't actually know this is enough to apply dominated convergence a lot of the time. So you can't apply dominated convergence from here, right? Because I don't know how big the FK are growing somehow.
So I use that first to show that f is in L1. Does that make sense? So what I'm saying is f is arbitrarily close. So like the absolute value of f is going to be as small or equal than the absolute value of fk plus some epsilon. And for k large on a set of measure one.
You don't actually know that because, for example, imagine I have fk that, how do I say this? What's a good counterexample? So let's imagine f is 0. This problem is somehow linear. So what I'm imagining is a kind of like a bump function, but they're like kind of growing, right? So if I have fk looks like this is f1, f2, 3, and they're kind of moving around, right? I don't actually know that this guy, like your argument will work here, I think. Does that make sense? Like, so in some sense, I need a little bit finer control in terms of the actual, like convergence almost everywhere is really weak in some sense, right? Because I could be converging, but I don't know, like you fix a set, like let's say on this set, I could be converging really, really slowly to my limiting thing somehow. Or yeah, and so if I don't have any control, I can't bound these things. Yeah.
Thanks.
Yeah. It's there's a distinction. So when I say fk converges to f almost everywhere, right? There's a few things that I like to think about like when these don't, so they converge almost everywhere. Let's say they don't converge in L1, right? So the one I like is the box function. So this is of height k. This is 1 over k, right? So I know that this guy pointwise converges almost everywhere to 0, right? There's a point here that's like infinity, but measures 0. So almost everywhere this converges to 0. When I take the norm of this guy, right, integral of fk, this is always going to be 1, right? And so I'll never be able to converge in L1. So somehow our problem, when it says, okay, I have behavior where I can split it at some finite level, and then I get good behavior, and then there's another set from below. You'll always see things like this about splitting basically above. Do I have some, can I split my behavior where I'm less than infinity and then above? Okay, good question. Any other questions about this type of problem? Okay. If not, let's do, I got another little fun problem that's related. 1 second. I'm going to pause the recording for 1 second. Because my computer is running out of batteries. I'm recording. Okay. So this other one is more of like a calculus problem. This is number 9 on the same section, so LP spaces and density. Okay, so if F is an L4 of R, show as lambda goes down to 1, the integral of f of lambda x minus f of x to the 4th dx goes to 0. Right, so what it's saying is if I scale my domain by a little bit, and I know my function is close in L4, then I should be good to go. Okay, and so there's a lot of different ways to do this. I'm going to do one way that's kind of, I don't know, the one I thought was entertaining. But yeah, if you think of another way, there are also other ways. So for a first start, let's just assume f is in C1, right? And we're kind of allowed to do this because these functions are dense. So this guy in L4 is dense. Is dense. So I'm kind of allowed to do this, right? By a triangle inequality and some approximation argument, I can get the same result if I assume f has one derivative. And then what I do is I rewrite this difference by the fundamental theorem of calculus to be this guy. Right? Okay. And so when I do this, I can take the 4th power norm, this guy to the 4, and then I know that this guy, so I can write this dt as a how do I say this? A probability measure. So I average over it. This is 1 over this guy from 1 to lambda. F prime tx dt to the 4th. And I know by Jensen's inequality, so x maps to x to the 4th is convex. Right? Because it looks like x squared, but a little closer to a little sharper, or a little flatter near 0. So if I apply Jensen to this thing, right, I get this guy out front, right, because it's just a constant. So I'm applying this to the 4th. And when I apply Jensen, I need that, okay, that this whole thing is the same as when I bring inside, it's less than or equal to when I bring the 4 onto the function. So here it's going to be f prime tx to the 4th dt from 1 to lambda. And there should be
And you still need a 1 over lambda minus 1.
I need a 1 over lambda. So yeah, I was just thinking that. So I need this to be a 3, right? Because I canceled one of them. Okay. So if I do this, and I have pointwise control now for almost every x, actually for every x, because f is in C infinity, I can integrate this guy. So let's do that. So I integrate an x, I get the thing I care about, to the fourth dx. This is going to be less than or equal to integral. So there's going to be these constants out front. There'll be a lambda minus 1 cubed integral of x, and then integral 1 to lambda f prime tx to the fourth dt. Okay. So when I do this, I get, I would like to, this dx. I would like to now flip orders of integration. So I use Houdini here, and I get 1 lambda integral f prime tx to the fourth dx dt. Okay. Now when I do this, let's change variables. If I have y equals tx, dy equals t dx, because I'm in 1D. So this guy is equal to lambda minus 1 cubed integral from 1 to lambda of, and then I'll get 1 over t, right? But then this guy will just be f prime. Everybody see what I'm just changing variables, and because I've multiplied by t, I get a 1 over t out front, right? Yeah. Okay. So when I do this, I'm going to t. I use that now this is a constant, f prime in L4, the fourth, 1 lambda, 1 over t dt. And I can actually integrate this guy. I know that this is the same thing. L4, 4, this is going to be log of lambda. So by group terms, it's going to be a log of lambda, lambda minus 1 cubed times f prime and L4, which is just some number. This is just some constant number. But the goal is, so if you can check that, okay, as lambda goes to 0, this is like third order. Sorry, as lambda goes to 1, right, this guy goes to 0. This whole thing goes to 0. So as lambda goes to 1, the right-hand side goes to 0. Is that clear to everybody? What's going on here? Yeah, I think it's kind of fun to see this kind of log popping out because it's just a change of variables at some point. That's what's happening. Okay. And why should I not be worried that there's a prime here?
Because the derivative is continuous and compactly supported.
Yeah, and so I'm good. I'm in L4 there. How do I know that when I'm taking this approximation, that doesn't flow up? That isn't so bad. Well, the reason, I mean, you got to check it, basically, is what I'm asking. So when I take this quantity, f lambda x minus f of x to the fourth, right? What I'm going to be using, let's just use the L4 norm, because I have a triangle inequality there. So what I'm doing is I have this, and then I want to say that, okay, I have an f lambda x minus, and then let's say there's some smooth function. What I'm doing is I'm doing triangle inequality to compare to my original thing. These are all L4. Because I know I have I have triangle inequality for LP spaces. Okay, and so this term, since I know that like continuous functions with one derivative, complex support are dense in this space, I can get this term to go to 0, right? This guy can be less than epsilon. But also this guy is also less than epsilon. Because if I do this change of variables again, right, I get a 1 over lambda. So the turns out to be this. So in the end, what I get is this guy is less than or equal to 1 plus 1 over lambda to the 1/4 epsilon plus, and then this difference of g. So that's the density argument, right? And lambda is greater than 1, so this denominator is fine. It doesn't blow up. For this part, right, we already showed that, okay, this guy is less than or equal to, and then we had some, like this was lambda minus 1 cubed log lambda, and then g prime in L4. And I think this is actually to the 1/4. Okay, but I still know, okay, because I fixed g now, I know that this guy goes to 0. So I don't have to worry. It's like, sorry, I'm just kind of doing a sanity check. Okay, my approximation didn't matter in the end. I highly recommend you do this for these problems. Because sometimes, if, for example, in my argument, I had accidentally used extra properties, right? Or done something here where I couldn't, like this step here, I had to do this little change of variables to check, oh, it doesn't blow up in epsilon as I do this. Okay, any questions about uh, this exercise? Okay, cool. Well, let's do one more, which is really short, and then I'll let you guys go. So this one is problem 17. Same section, healthy spaces. So what it is H, let's just say going from R to R, bounded, measurable, and for all intervals I, intervals, what I have is this guy, integral of H, is less than or equal to the measure of I to the 1/2. Okay, now we're going to define this thing, which is like mollification. But what I'm doing is I define H epsilon to be x divided by epsilon. So what's happening is if I think of epsilon as being small, right, x has to traverse a larger range of things. Sorry, a smaller range of things in order to look the same. So it's kind of, as epsilon goes to 0, it's compressing H in the domain, right? So I'm squeezing the domain together. I'll just draw the picture. So if H looks like this, then H epsilon looks like this, right? Where this factor scales by epsilon. So it's like squeezing it a little bit. Okay. So if I have this, show for all A measurable sets. So I'll write this. There's like measurable sets in R. So this B stands for Borel measurable sets. Doesn't really matter. I'm just saying measurable sets. With A being finite measure, then the integral of H epsilon goes to 0 as epsilon goes to 0. Okay, so our goal is to show that when I take the sequence of H epsilons, I actually don't pick up anything subject to this constraint. Okay, so the first thing to check is what happens to H epsilon under this condition, right? This is kind of like a magical condition. I don't really understand what it means. So let's see what we can do. So notice that if I integrate on some interval I, H epsilon, so this guy, well, I can rewrite this as, by definition, x over epsilon dx, same interval. But now, if I let y equal x over epsilon, dy equals 1 over epsilon dx. So this guy is equal to, there'll be an epsilon out front, integral I over epsilon, right? Because I'm integrating over this new set each of y dy. Right? Okay, and now I take absolute values everywhere. I know that from my condition, this holds for any interval. So in particular, it holds for I over epsilon. I can do this inequality. So this guy is going to be less than or equal to epsilon times, and then what did I have? I had I over epsilon to the 1/2. Okay, and so what this means is I get actually, there's a half in the denominator, half up top. There's an epsilon to the 1/2 up here. Okay. So actually the integral, so taking the limit, taking epsilon to 0, you can show that these guys, h epsilon of x dx goes to 0 as epsilon goes to 0. Yeah. Right. Okay. And now the last little step, if you give me any measurable a with finite measure, how do I upgrade this? So this is a statement about intervals. How do I upgrade it to a statement about the whole thing? And it should be fairly intuitive that, well, all I have to do is approximate whatever my set is by intervals. So let's say I have some crazy set of the real line. No matter what, I can always find, by the definition of Lebesgue measure, there exists, I should write it like with an epsilon. So let's say eta be greater than 0, be our kind of error for how much off of the set I am. So given A, which is a measurable set, I can always approximate A by a sequence of intervals, right? This is the kind of the first thing we talked about, such that when I look at the measure of these guys, ik, and I look at, how do I want to say it? Like this. Yeah, so these guys cover, so this difference should be less than eta, right? So the idea is I have some crazy set. I usually like drawing them 3D. So yeah, I have some crazy set of points. And what I'm doing is I'm just saying, okay, I can approximate the measure pretty well. Okay. So now, okay, I do this. I know that since A is finite, so without loss of generality, IKs can be, I say this. So A being finite implies that continuity of measure shows that I want to say this happens. There's some k, large k interval. So this is I, okay? is less than like 2 eta, 2 eta. So I'm approximating my infinite sequence of things by a finite collection of intervals, right? Giving up some small eta. Okay. Now, if I do this, I can rewrite my whole set. So let's call this part AK. It's somehow like my approximation. So when I integrate over A for some set A, well, I can look at the part which is in A. I should call this capital K. A capital K. Right? And this is still H epsilon plus integral of this guy on A minus AK. Or AK minus A. Sorry. One of them is bigger than the other. I should write like this. It's this. A minus AK. Okay. Now I know that my function is bounded, right? So this guy, no matter what, is bounded by H, the like maximum it could be, times whatever the measure of the set is. Right? For this other part, I know that this guy is less than or equal to this is going to be the sum, k goes from 1 to capital K, of I k's. Right? So I'm patching together the little lemma that I had before. Because I know AK is this union of intervals. Okay, so I know that this guy goes to 0. Right? As epsilon goes to 0. Epsilon's kind of independent of K. K goes to infinity. K goes to epsilon goes to 0. This guy goes to 0 as epsilon goes to 0. This guy is less than because I know for that this sequence of intervals approximates, right? I think I might have this a little backwards. That's okay. But the difference of these guys, even if I write it like this, or this is like the symmetric difference. But this difference of two sets is going to be less than 2 eta, say. Okay, so what we've shown is the limit, lim sup, epsilon goes to 0 of these guys. It's less than or equal to, I know this term goes to 0, plus, and then it'll be the L infinity bound of H. So the supremum norm. Times this difference. So whatever part was not in these intervals. And I know that this guy I can make less than H times like 2 eta. And since eta was arbitrary, I know that this whole thing goes to 0. Okay. Any questions about that? Okay, perfect. Well, okay, our last little lecture is going to be on Friday, same time in the morning. Yeah, I'll see you then.